Hello, hi. My name is Lav Kumar. So today we are going to discuss about the one of the complex algorithm and lengthy algorithm with a lot of concepts. That is the support vector machine. So I'm trying to explain step by step by using my PPT. Quickly share my screen, and yeah, here my PPT. Yeah, yes. So support vector machine. Before going to this concept, let's try to understand what exactly does means the vector. So in your inter or in your BTech, you are maybe aware about this term vector, right? So let's say there are the two students are there, student number one and the student number two, they have the marks for the subjects number one and the subject two, like 60 marks and the 70 marks out of 100 marks and the 70 out of 70 and the 80 out of 100. If you're converting these things into the vectors and you can make it as vectors and you can make the calculation, right? You made it in the new inter and as well as the BTech in the graduation, right? So the same concept people are using here, and they will take the consideration of the support of those vectors and they create a machine learning algorithm that is the support vector machine. We will see one by one what exactly this, what does it mean, where to use, and here I'm going to explain you about the what is the meaning of the machine learning and the support vector machine means, when to use, and what are the types and the key terminology. This is really help to understand the what is the terminology used here. Then can keenly understand this and the step-by-step workflow, the linear support vector machine, and the two more concepts inside that linear support vector machine. That's the soft margin and the hard margin, and the non-linear SVM with the kernel ticks, right? How you're dealing with the non-linear SVM and how the kernel tricks are helpful there. And there are the four tricks are there. I will going to explain about them and the complete project flow, how the project flow will be there. Let's say if you are taking a problem statement and if you are applying on the support vector machine, what exactly steps to follow, right? And what are the advantages and disadvantages of SVM, when to use, when not to use. Based on this, you can understand that real world applications also I'm giving here and the summary. Let's see. So, before going to that, let's see the machine learning means itself. Right, already the people are trying to train a machine with the experienced or the existing data to make the prediction. That's the machine learning, and the support vector machine is the one of the machine learning algorithm. So, why do we need this SVM is sometimes the data and the features are really huge, the complexity getting increased. Let's say if you have the 50 columns are there, 50 features are there, and really good. If it is 70 are good. If it is 200, what you have to do? If it is 1000, what you have to do? The complexity getting increased, right? That time the uh, traditional algorithms are really struggle to make the separation and clear to make the predictions. That time this SVM will clearly do the separation, finding the best dividing boundary. Let's see what does it mean also. And the support vector machine is the machine learning algorithm used to classification and regression. This is already you know. But what exactly does is it finds the best hyperplane between the separation of the classes. Let's say there are the two classes are there. This is one street and this is another street is separated by the a clear road. You can understand this is also as the this is the concept is actually taken here to separating the two classes. How the two streets are separated by a road. The same thing is taken here. Let's see how it is happen is the maximum distance we will find here. how it is work is the maximum boundary distance will separated by the road in the colonies. In the similar fashion here also it will done between the data points, and you'll find those nearest data points is called as the support vectors. We will see each and everything how it look like is also. Let's see one simple diagram to understand. And of course, through this, we have the two types of SVM survey. One is the linear and the another one is the non-linear SVM. Let's see linear algorithm. See linear SVM is looking like this. It is having this is the class 1 and this is the class 2. And these classes are separating by this line. This is the line is you can say perfect the linear line, right? Because the linearly separable because of they have the linear relation between them, and it is used for the few classes or the more classes also. And basically it is works, the linear SVM works for the 2D lines and the 3D plane also it can draw. But the linear SVM will be used for the when the features are the, let's say, the columns, the column number 1 and the column number 2 and the column number 3 are the target variable. When they have the linear relation, then it's really useful. You can do with this linear support vector machine very easily. Okay. And let's see what exactly the nonlinear SVM. This is the second one. So generally in the real-time scenarios, what happens is we don't have the, let's see here, the examples wise, the cats and dogs, the data is really simpler, right? The simpler data, and you can easily separate the data by using this linear SVM. But in the nonlinear, what happens is the data is not really following the linearity relation between the variables. So see image classification kind of things and the medical diagnosis, they have the complex of the data, complex columns. So that's the reason people use the nonlinear SVM. And that time the kernel trick is really helpful. Let's see, in the real world applications, the data, let's say this is the one class and this is the another class, this complete data points. And if you're using the kernel trick, what happens is it separates the by using the hyperplane between these two things very clearly. This is the way the non-linear support vector machine uses the kernel trick to find the best hyperplane between the classes. Let's see all the kernel trick, what does it mean and how to apply that also. Okay. And coming back to SVM, so what exactly the terminology is there? Let's say there are the class 1 is there. This is the one class. Let's say these all are, you can say, spam mails. Spam mails. And these are the important mails. You can say ham mails. Ham mails. See, here, what is the line is clearly separating the two classes, that is called as the optimal hyperplane. But okay, boss, what about this? What about these points on these lines? These two lines, you can call it as the marginal lines. How do you know? How do you say this? Because the lines who are the falling on these data points are nothing but which are near to the hyperplane. They called as the support vectors. They are the vectors. And if you draw the lines through them, you can call it as the marginal lines. Let's say here, hyperplane is the decision boundary which is separating the two classes. In 2D, it is looking like a line. In 3D, it is looking like it's a plane. In the more than 3 dimensionals, it is looking like a hyperplane. But what about this? The support vectors, the data points that close to the hyperplane. Here you can see they're very close to the this optimal hyperplane. That's the reason they considered as the support vector. They are really supporting to the positioning that boundary so clearly separation. That's the reason they are the called as the support vectors. Then whatever the distance between the hyperplane and the nearest data points, the support vectors of the each side, you can maximizing that line. See, this is nothing but the margin. This is, you can say, this is the margin. See, the whatever the distance you are maintaining between the two margin lines, that is the, you can say, margin. Sorry. Yeah. And the, what about this maximum margin is this is like the best hyperplane, which is the separating the largest margin, and it clearly separating the two classes. Let's say there is a street is there. There are the two streets are there, and the two streets are separated by a simple, very narrow down path. Even you confused. Let's say if you are using the Google Maps, Google Map also confused. And if you are the two streets are very clearly separated by the a great highway path or way, very good roadway, then the Google Map also easily can find the which is the street and which side of the street. This is generally happening, right? Even physically you are going there for the small path, you don't know which street is you are belonging to. You're a little confused. If you're clearly separated by road, you can easily find that separation, right? So that is achieved by this maximum margin, like a clear road path between the two classes. Okay, in real time scenario, let's say there are the two type of students are there. The people are pass and the people are fail. If you are making the separation between them, these guys are pass, these guys are fail. This is the hyperplane, and these are the margin lines, and this is, you can say, the maximum margin. And this is clearly separation between these two, pass and fail. Then you can clearly separating this. So this is only the concept is really working, but we need to understand how to do that. That is only the thing. Let's see how to do this clear separation, right? These guys are, let's say, pass. These guys are fail, right? So where to draw this optimal hyperplane? Here, here like this, or here? Don't know, right? Little confusing, right? So this is what we need to understand. So by drawing with a pen is very easy, but how it is really happening with the, sorry. So how it is really happening with the in the real time scenarios, right? That's the very important thing. So we need to find the optimal hyperplane. That's very important. So for this, we will use the some mathematical intuition here. Let's see the how they're working. This is what the, so let's say you can draw this. Okay, my drawing is a little hectic. Okay, uh, okay, don't consider this. So let's say this is the one class, this is the another class. What happened is, so generally the equation for the line is y equals to mx plus b. This is the thing we will use it here. The same thing. So generally not one single feature is there. That's the reason w1 x1 plus w2 x2 plus and so on plus b equals to 0. So people are converting this into w transpose x plus b equals to 0 is the one thing. And if it is greater than 0 is something and less than or equal is something. So let's see what is this, how this function is working here. Let's say that's the reason we will take one functionality here. W transpose X plus the W naught is equals to 0. This is where the data points where the located. This is we can consider as the hyperplane. This is the optimal one, clearly separating the two classes. Okay. And what about this class, the positive class or above class? This thing, when the value is greater than 0, that comes under this class, positive class. If it is less than this, let's say W transpose X plus W naught is less than 0, that comes under to this area, right? So this is the way the hyperplane will be achieved. Fine. So if you are combiningly, you can see this complete thing. So this complete thing, the equation followed by the W transpose X plus W naught greater than 0. This is the positive class, and the negative class. We will follow this. We will pass the all the data points to here, and then we will achieve this negative data points, and also we'll find this hyperplane, which is the separating the both the classes very clearly. That is the maximum separating margin. We clearly find this. But what about these marginal lines? How to draw these marginal lines? This is also one important case, right? Let's see. We till now we will achieve this optimal hyperplane by using these equations. Okay, cool, fine. So how to achieve this hyper? So the marginal lines which are falling on the support vectors. So these are the equations will helpful. The same equations I'm using here. So, but what happen is we need to find the maximum of the distance between these two. The maximum of the distance between these two. But how it is possible? How can we find this? How we get this 2 by mod and what exactly this b by mod? So this is the magnitude and the distance of this between these two marginal lines. You will see, this is the one class. We can say this is the positive class and this is the negative class. So, oh, sorry, this is the blue thing. You can say this is the positive class and this is the negative class. So two things, and we already achieved this hyperplane. But our issue here is now is we are trying to find these marginal lines with maximum separation. The maximum separation, we're trying to find this. So how to achieve this, right? We just need to find the distance between them. That's it. We'll first figure out these support vectors. Then we will draw a line by using this equation and this equation. Wx minus b equals to 1 and equals to minus 1 negative class. The one is the positive class. By using these equations only we can find. Let's see the mathematical thing. So the distance is between these two, you can call it as the projected distance. Why you call as this projected distance? How we can achieve is we can use the dot product here. Okay. Let's say this is the one data point I am taking it as the x1. This is the another one is the x2. And here the distance between these two data points is the x2 minus x1 and the direction is the w I am taken here. Okay, fine. But what is the thing we are using here is in for finding the distance while using the vectors, we will use a simple formula. The dot product of that difference and the direction and the magnitude of that. So that is what I am building here. X2 minus x1 and the dot product into w, the direction and the magnitude of that. So we just multiplying both of them, x2 w direction and the minus x1 w direction by this is the magnitude I will make it this one as the equation 1. And here we will use in support vector machine, this is one equation for hyperplane for these two data points. This is the equation generally used. Wx, this is like looking like a mx plus b. So the line equation here. So this is, you can say, positive side, and this is the positive side area and the negative side area. You can take it here in the y. Let's see further calculation here. So what is our issue is we need to find this x1 w direction, the x2 w direction. We need to achieve this. For this, we need to use this formula, the same formula, the y star for the, so wx plus b equals to 0. This equation we are going to use. If it is 1, that is for the positive class, the 1. So same thing, the y I'm replacing with 1 here. In the w x1 plus b equals to 0. Why I'm considering this? Because of this is the area I'm going to find. Okay, so that's the reason w x1 plus b equals to 1. I'm taking this equation and I'm just sending this b to that side, and the w x1 equals to 1 minus b. This is the equation 2. Now I got the w x1 here. So what about the w x2? You need to find that one also, right? So that's the reason I will take the negative side. That's the reason y is the negative minus 1. So I'm just replacing this with minus 1. That's the reason minus 1 wx2 plus b, because this is the data point negative side. That's the reason. So wx2 equals to minus b, because I'm sending this minus b that side, and I'm sending this minus 1 also to that side. First I'm sending this one, then I'm sending this minus b. That's the reason. This is w direction of that x2, because now we achieve these two things. Two equations I will replace into this equation 1. This is our equation 1. This is the x2w minus x1w by magnitude of the w. So I'm replacing with them, and after making the calculation, now I got this 2w. This is what we achieve. That's the reason I'm showing here to the direction with the 2 by the magnitude of w, right? So this is the way you can use the vectors. So now we achieve that the max of the distance between the margins. So by making this simple equation, argmax w star, comma b star into 2 by mod, can such way that we will achieve by using this equation of this distance, right? Let's see how to apply those data points. Let's say I have a simple data points, and how to apply those data points on the w1 x1 and w2 x2. So let's say I'm already told you now. So this one, so w transpose x plus b equals to 0. This thing we can convert into w1 x1 plus w2 x2 feature, and so on, right? We can use this, right? We will use this equation, and we will try to understand the how exactly the separation will be happen for this by using, this is the generalized equation. You can call it as the generalized equation. And by using this equation, how these classes will be separated, I made a simple calculation here in this table. Let's say I have the feature 1 and the feature 2. This, let's say this is belongs to the loan thing. The people are eligible for the loan or not. Let's say this is the one class. Sorry, this is the one feature and this is the another feature. By applying these features into that equation, this is the equation I'm going to use. W1 x1, so w1 x1 plus w2 x2 minus e equals to 0. See here, these are the values W1 0.5, W2 is it's a 1, and the B value also I'm putting here, so it's a plus. I'm putting here. And now it's a fixed value 0.5 and the WT is the 1 and the B is the minus 2.5. Let's see what it is belongs to. G of X belongs to positive class or negative class. We will decide here. Okay, let's see. We will one by one apply. This is the point 1. If I'm putting here and the X2 it's a 2. It's a 0.5 plus it's a 2 minus 2.5. It becomes the 0. The same value g of x is I'm getting here. This is the perfect hyperplane, right? This is the perfect hyperplane. The same fashion will give the 2 and 3 here. The 2 0.5 2 plus the 1 into 3 minus 2.5. It's a 1 plus 3, it's a 4 minus 2.5, it's a 2.5, so value, it belongs to the positive, it belongs to the positive margin, right? Sorry, it's a 1.5 in result, right? It's a, now it's correct. So this is the way we will we will send these pass the complete all the values to this equation and separating the classes of the all the data points positive and the negative and the on the hyperplane. This is the way we will do this. Okay. How it exactly one by one it is working is for the linear SVM is the first we'll plot all the data points we will in the space. The space means the plane where it is existing. We will plot all the data and we will find the support vectors, right? Whatever the support vectors are there, we need to find them. Whatever the support vectors are there, the closest data point first we will find. And after that, we'll draw the positive margin and the negative margin. Then we'll find the maximize the margin, positive margin and the negative margin. And then we'll classify the data by the optimal hyperplane. So this is the way the linear support vector machine will be working, and the complete data will be trained, and if the new data point will come, it will clearly separate. Let's see. Let's say this is the one simple example. Let's say I have the label data, the test data and train data and test data and the test data, right? Sending to the algorithm. This is my SVM. It will be trained by using this all these steps, right? Now, after processing, it will classify the so clearly the elephant, camel, and cloud. Oh, very clearly it will separate it, right? So, nice. So, this is the way linear support vector machine will be worked and trained, and if new data point will be coming here. Let's say if the new data point will be coming here, and now also this is already trained, so it will clearly separate. So this is belongs to which class, this is belongs to which class, or this is belongs to which class. This is like a unknown data. We don't know what exactly this result is. We just pass the data to the algorithm. It will pre-processed and now we will get the output, and the output will be predicted by the trained SVM. Okay. Let's see. There are some issues with the linear SVM. So till now we are achieving this argmin or argmax with the we're using this equation. Okay, fine. But there are the a simple issue is there. So not every time we are not easily achieve this. We are not easily achieve this much clear separation. And what happens is the maximized distance is not so easy to achieve. And what happens is in general cases, the distance between the two margin lines is very, very low. Very low. Because of this, if any new data point is entered, what happens is it is really getting confused. Am I belongs to this class or this class? Am I belongs to fail class or success class? Or am I belongs to the can apply for the loan or am not apply for the not for the loan, right? So for that time we need to achieve maximize line, but there are some misclassifications may be happening. If you are maximize this line, what happen is some negative classes are comes to the positive class. Some positive classes are going to the negative class. This misclassification may be happen. Fine, but we need to handle them. We need to handle them and we need to achieve the perfect model every time. So for that, we have the concept of the hard margin and the soft margin. So to achieve the generalized model to sending the any type of data, I can easily separable the two classes. That is means the generalized model. It really works very well on the new unseen data points. So that is called as a generalized model. To achieve this, we will try to understand what is meant by this hard margin and soft margin. So which is we need to achieve, right? See, where there is the zero misclassification is there, that is comes under this hard margin. Means this one is hard margin and this distance is very low and model is not achieve the generalization. Perfect separation is there, that's really good. Okay. The work only when the data is perfectly separable, then only we can achieve this. And it's really very sensitive to the outliers. If there any outliers are there between the two classes, it's really hard to find. And it's rarely used in the real-time scenarios. People are using the soft margin, but how to achieve this? So let's try to understand what is meant by this. It's really allow the misclassification. So how here the classes of the negative entered into positive and positive into negative, we are allowing that. We will introduce a term zeta and we'll control this zeta term using this hyperplane. And if the C is high, it's nothing but hard margin. So, and if it is C is very low, it's really flexible, looking like a soft margin and clearly separable. And you can easily achieve this generalized model and you can send any type of data and clear separation will be happening. What exactly this zeta is? This is the zeta. So this is the arc mean, the W by 2, this is already we achieved the distance and we give the plus. So after making a lot of mathematical equations, statisticians and the mathematicians are creating this. The scientists are creating this with the hyperparameter along with this zeta. Right? Let's see if the value is high or low, how we can understand this zeta is. If it is a zero, the classification is really correctly classified. The zeta value is 0 and 1, and the value are inside the margin. And if the value is equals to 0, the zeta value is equals to 1, the decision boundary. That is in the decision boundary. The data point is there in the decision boundary. And if it is greater than 1, it was wrongly classified. Means we already have this, right? Already have this two margin lines and the hyperplane and this is the positive class and negative class, right? So the correct classification comes under this. And the inside margins, sometimes the sum of them are existing here, that is in between 0 to 1. The on the decision boundary, and if it is something like greater than 1, that's they are like a greater than 1. From this you can easily remove or eliminate or decrease the misclassified classification data points, and we can easily achieve the correctly classified and the hyperplane and perfect margin lines also achieved. And the soft margin will works very well and generalized model will be achieved here, right? So till now we are understanding the how the linear SVM will be working. But in real time scenarios, it is not there really. The data is following the linearity. That time we will use this non-linear method, the second SVM type 2. The most of the real cases are not linearly separable. So it's true. But how to do that? That time you have the kernel trick is there. What exactly this kernel trick is? We will transform the data into higher dimension. What is meant by that, Lokman? Let's see that kernel trick also. But we'll try to understand that there are four tricks are there. The one is the linear kernel trick and the polynomial kernel trick and the RBF radial basis. This is the one, and the Gaussian kernel trick and the sigmoid kernel trick. Radial basis function or the Gaussian kernel trick. This is the more popular. People are using this. These are less used, but these tricks also determine the scientists. You need to understand what exactly I mean. Which we'll see one by one. So, what exactly the kernel? What is this kernel in the non-linear SVM? See, let's say if you are just giving the data points, if the data points are looking like this, if you are using the kernel trick, it will separate the data points, and this is the manner. It creates a path for this and it's separating for this, and this is under the one class, this is under the another class separated by line. After applying this kernel trick, what kernel trick will be do is it will separate the non-linear data points into linear classifier. How it will do that is it simply do that into the transform input data into higher dimension space. See it, if it is the two dimension, let's see. What we do is we will apply this 2D into 3D. The 3D, what happens is we have the one more thing, or one more thing. Or if it is a 4D, one more dimension is there. So that time it is clearly separable. But we are not doing any mathematical thing here, but we are just doing the dot operation and finding the higher dimensional space, and we are separating them by using this trick. This is really good approach to the classification, and efficiently we can do this. And let's say this kind of data is there. So this is very hard to separating our classes, right? So that time we'll use if I apply the kernel trick on this data point, what it does is after sending them to higher dimensional space, the one class is on the top, another class is the down, and the decision surface will be separating the two classes so clearly, right? This is the way we will achieve this, the clear separation for the non-linear support vector machine by using kernel, right? I hope you really understand this, how you are sending this 2D to the higher dimensions. Okay. Let's say this linear and the polynomial and the radial basis function and the sigmoid. They are following these equations. Let's see each and everything clearly. So linear kernel is looking like the linear support vector machine. This is a simple dot operation between these two, right? Two data points. So there is no transformation will be happening because it's a 2D, but for the data, so linearly separable. And that's a simple linear SVM. And when to use this, the text classification is there, higher dimensional sparse data is there for the NLP. We will use this kind of trick. In the code, kernel parameter is there. In the kernel, we can just put the linear in the coding actually. Let's say the second one is the sigmoid kernel. So it follows this formula tan h of the alpha x of transform y plus x. It follows this and it looking like this. And this is the way it is separating the classes, and the x and y are the nothing but the input vectors, and the alpha is that the scaling parameters, and the c is the bias, nothing but offset, right? Sigmoid kernel will be inspired from the neural networks. So how the activation function, tanh nodal function will be working? Sorry, the sigmoid will be taken from that. Yeah, so it behaves like a activation function. That's the reason it is looking like this, and the formula looking like a tanh functionality. And the third one is the polynomial. So it follows the xi plus, sorry, xi dot xj plus c and the power of the d. So it's a dimensionality, the degree of polynomial, and the c is the constant, and the x and the these are the vectors. So the main intuition here is the we need to find the curvy decision boundaries. So wherever the curvy decision boundaries are there, it follows means that directly you can say yes, it is following the polynomial kernel. Okay, when it is used the when to use is the relation of the polynomial when it is data is curvily separated, that time it use we can use this polynomial, and the instead of straight line we can simply draw the this curve, right? And RBF, the Gaussian kernel is the people are using most popularly used. So it will use the exponential or the minus y and the vectors with the magnitude of the squaring of them. So the points are close. The main intuition here is the points are close together in the high similarity, and the points are far separated low similarity. Means, see here we have the different data points, different classes. This is one class. This is another class. So what we can do is these all data points are similar, and we are bringing all the similar data points together, and the higher and lower we are using that concept, and where low similarity data points and the high similarity data points we will separating them so clearly looking like this, and we will use this. Why it is popular is it will be used for the nonlinear data sets, and the most real problems we can easily solve by using this trick, RBF method. And each data point creates the bubble influence looking like this. The gamma is nothing but it's the kernel width parameter. So this width you can say the gamma. And it is mostly working with the similarity of the lower and the higher. So this is the way the Gaussian will be separating in the Gaussian space between the two classes. Wow. So this is the when the nonlinear support vector machine will be working till now. So by using all the kernel tricks, by applying the passing all the data points to the linear or the polynomial or the RBF, right? So let's say if you are working with a project by using support vector machine, what exactly the steps you need to follow is first we need to understand the data. We'll prepare the complete data, importing the data set and handling the missing values and the normalize and the scale all the features. Then we will split the complete data. It's like a X train and the test data, right? 80% of the training and 20% of the test data. Then we will first select the which kernel you are going to use. Generally, we will use the RBF, right? So we'll select the kernel inside the coding part. The coding part, it will gives the parameter kernel, and but then you can train the algorithm. So algorithm will find the max margin and the hyperplanes by using the support vectors. Okay. So whatever the calculation we have done till now, the complete thing will be we are understanding here. So whatever the things we are discussing on the top, the complete thing happening here, the complete inherently happening here, the training of the model and the optimizing this model so we can maximize the margin, the distance between the support vectors by using the optimize the hyperplane. And by using this C and the zeta, we will handle the misclassifications, the slack variable. So we can tune this, and the misclassifications will be reducing, which are the greater than the one that is comes under the misclassification, we will mostly delete the, and then we will do the predictions. Then we will send the new data point and we will make the predictions, right? Let's say the particular person is having any risk of the future, having getting any kind of diseases or not. We can make the prediction. After 10 years, what happened? Right? We can make the prediction. We will already train such kind of data. The SVM will be predicting that. And we need to evaluate the model, how accurately our model will be working. We will use the precision, recall, and F1 scores and the accuracy. These are the evaluators we will use. Okay. And what are the advantages of the support vector machine is? So it can work with the complex data and work with the high dimensional spaces, and it's easily avoiding the overfittings. And the Vercel working with the kernel tricks, because kernel trick is not mathematically really working. So it is just doing the dot point and the low dimensional to the high dimensional space. It will find, okay, the data will be separating on the top and the lower. It is clearly create the hyperplane between them. That's it is doing. Okay, because of this, it's really cool. And the robust for the outliers. Outliers problem we can easily achieve here because the separation of the data points are there, right? The hyperplanes are there. So because of that, you can easily understand where the outliers are there. Because of that, the model will be working for very robust to the outliers. Oh, disadvantages. So because of the large data points, the large data set, it is very slow down. And sometimes we will find difficulty to find the which is the right kernel point and the hyperplanes of the C and the gamma. And we need to make some trials and then we can achieve this. But this is not so easy sometimes. Difficult to tune this. And sometimes any overlapping of the classes are very huge. That times we will get the very poor performance. And so we're feeling like a black box of this model. We don't know what is really happening inside after giving the complete data points in the training and making the prediction also. Looking like a sometimes feeling like a black box model, right? And we must store all the support vectors. Because of that, the memory is feeling like a very intensive. So we need to have the more and more memory while dealing with the SVM. So the some of the disadvantages also there, but fine. But where we are using the support vector machine is text classification, where the Gmail spam detection, sentiment analysis, movie reviews, right? And the image classification and the object detection and the fraud detection, the credit card fraud detections, this kind of data, and the medical diagnosis, because these are also having the all the complex of the data. That's the reason people are using this. And where exactly the house price prediction for we can use the support vector regression also. Of course, I'm completely most aligned to the classification, but okay, Kuba, but what about the support vector regression? So here, what happens is, if I simply explain, so we will use the anomaly SVM for the anomaly detection also, fine. But support vector regression, how it is working is, so all the data points are looking like this. Similar fashion, we'll find the best fit line. The best fit line we will find, then we can use this support vector regressor for the regression data also. Okay. And coming to this, what exactly we are learning is what is meant by support vector machine and how it is the finding the hyperplane and the support vectors which are closest data points to the defining to the margin, and the linear support vector machine linearly separating the data. This is also we are understand till now, and the hard margin and the soft margin and the kernel tricks we will understand, and the where exactly SVM is really excellently working, how it is working, right? The real-time applications also like spam detection, image recognition, fraud detection, and medical diagnosis also. Okay, this is the way. Thank you guys. So this is the way we can understand this so clearly. So thank you guys. Thanks for understanding this. So thanks for bearing with me. And if you have doubts, so you can ask me in the chat. And if you want more and more things, also you can ask me. And if you have anything related to the machine learning, also you can ask me any type of concept also. And subscribe my channel. Thank you. Thank you guys. Bye bye.